Okay, I'm going to spend some time going through paper 2 of the GCSE Separates Chemistry for AQA. It's the June 2022 paper. My intention is to go through all the answers to this paper as quickly as I can, but also explaining why I've chosen the answers that I have and kind of giving you some extra information as I go. So, as I say, paper 2 for Separates higher tier June 2022. So question 1 was about copper wire and copper compounds. We're given this polymer, polybutene, and we have to draw the displayed structural formula of butene. So the first thing we need to know here is that butene is an alkene, and that butene tells us we have 4 carbons. So we already have our 4 carbons here. We just need to make this into an alkene. And when we go from a monomer to a polymer, we also have our double bond in the center here, and then we make up the rest of our bonds, and we always double check that each carbon is making 4 bonds. So 1, 2, 3, 4, 1, 2, 3, 4. You get 1 mark for the double bond in the middle and 1 mark for the bonds here. We then go on to the next page, on to question 1.2, suggests why polybutene insulation must be removed from scrap copper wire before the copper is recycled. And the reason we do this is because the copper would be impure. So we want to make that recycling process as easy as we can by keeping the copper as pure as we can get it before we start. Describe how scrap copper wire can be recycled to make copper water pipes. Well, the copper needs to be melted for mark 1, and then it needs to be reformed or recast to pipes for mark 2. Wherever there's more than 1 mark for a question, I'll try and show you where each of those marks come from. There will be times where I give you more points on what there are marks, just to show you what the mark scheme would allow. Number 1.4 suggests 2 reasons why recycling scrap copper is more sustainable than extracting copper from copper ores. So the first one is we're using less energy, so that's the main reason why we do it. And the second reason why it's producing less waste, so less going to landfill, and it's a bit more sustainable for us. Next page, which is 1.5. I know I'm going quite quickly, but there's a lot to get through. This is about ion tests. There's always some sort of ion test in here. For these, you can't get the result mark without getting the first mark. So it's either 0, 1 if you get this but not the result, but you can't get 1 mark just for the result. A solution added will be sodium hydroxide, or NaOH. And the result when we add sodium hydroxide to copper sulfate solution to test for copper 2 ions is a blue precipitate, or a blue solid. And next, we'll describe 1 test to show the presence of sulfate ions in copper sulfate solution. We can add barium chloride, or BaCl2, and we should see a white precipitate formed. Cool, so that's the first question out of 11 marks. Question 2. So question 2 gives us some information to start with. A student investigated the change in mass when hydrated cobalt chloride was heated, and it tells you the method they use and gives you the results that they have. I think we might need to see some of this table to answer this one. Question 2.1 asks us to determine the mass of the empty test tube. It tells us in the method at the top here that 2 grams of hydrated cobalt chloride was used. So if the test tube plus its contents is 26.5 minus the 2 grams that we've added of hydrated cobalt chloride, our empty test tube must be 24.5, and that's a 1 marker. Explain why the mass of the test tube and the contents decreased. Again, we're going back to the top to this equation, which tells us that water is produced. So why is the mass decreased? Water vapour is produced, which escapes the reaction vessel. So that'll be 1 mark for each of those statements. 2.3 suggests why the test tube and its contents were heated until the mass did not change, and that is to ensure the reaction is complete. And then we're going over the page again, so I'll get rid of this page. We then have our calculation, the first of our math skills. When 238 grams of hydrated cobalt chloride is heated until the mass does not change, 88.1 kilojoules of energy is taken in. The student heated 2 grams of hydrated cobalt chloride until the mass did not change. Calculate the energy taken in. Give your answer to 3 significant figures. You will get 1 mark for rounding in this question. Now, I think I do this a slightly different way to the exam board do it, so I'll show you my way and their way. So this is the AQA way. This is the Mr. Hendry way. So the way that I would do it is we're trying to work out, or I worked out the kilojoules for 1 gram and then times that by 2. So 88.1 kilojoules divided by 238 grams gave us 0.370. So that's kilojoules per gram. I then have 2 grams. So I'm going to get an answer of 0.740336, etc., which to 3 significant figures is 0.740 kilojoules, which does match what AQA got. Their way of doing it was to take the mass of hydrated cobalt chloride and divide that by the total mass, or the mass given, and times by 88.1, which gave us 0.740336, and we get a mark for rounding. So mark 3 for rounding, mark 2 for an answer, mark 1 for using the values in the question. What type of reaction takes place when hydrated cobalt chloride is heated? Endothermic was the correct answer, but reversible was allowed. So that was one of the options given at the side of the mark scheme. Cool. We're already on to question 3, which is fantastic. And question 3 is our first 6-mark question. I think maybe the only 6-mark question in this one, which is asking us about a life cycle assessment. Now, there is quite a lot to think about in this life cycle assessment. We're looking at whether milk bottles should be made from glass or polymer. We've given some information about various different things, and we need to use the features of life cycle assessments in our answers to evaluate the use of glass compared with the use of polymer. So, we do need to make a judgment at some point in this. You do not need to write in full sentences necessarily, but you do need to cover as much as you can here. We need to give knowledge from the table as well as linkages to our outside knowledge alongside this. So I'm going to write my answer. I'll kind of speak through as I'm going where I'm getting the information from. So polymers require less energy. Polymers require less energy to produce, or less energy is required to produce polymer bottles and process the raw materials. So we're going to use less fuels. So using those less fuels is going to help us in environmental standing for an LCA. We also have, so that is from here. We also have the fact that the mass of the bottle is less. So polymer bottles weigh less, so less transport cost per bottle. That's both cost of transport and the fuel cost as well. I've then chosen this point for my third thing. Both glass and polymer bottles are recyclable. But recycling the polymer protects a finite resource. Which is beneficial. We can then look at this for our fourth point. You can say glass can be reused, but energy will be needed to transport and wash the bottles. So it's not just a case of fill them back up with milk straight away. I'm going to have to go on to my next page, but I'll show you the answer altogether towards the end. We'll then say some extra energy, crude oil, is finite, so it will run out. And we'll also say limestone quarrying can lead to air pollution and environmental concerns. So that's not a great thing either. From all these, we then, if we're getting into 5 or 6 marks, we need to give a reasoned judgment. So overall, I actually think polymers, I was going to write glass, are better, as despite crude oil being finite, less energy is needed to transport and produce these. You could make an argument either way as long as you've given your reasons throughout. 3.2 is a bit of a weird question because it's asking us about density. This is more on our math skills about rearranging an equation. We're asked to calculate the mass of the carton given the volume and the density. So the first thing I would do is rearrange the equation. Mass is going to be equal to density multiply volume, which is actually Mark 1. Mark 2 is inputting our values from the question. The density is 0.4. The volume is 40 centimetres cubed, so that's Mark 2. And Mark 3 is getting our answer, which is 16, and popping it on the line here for our third mark. Cool, that's all that there is to question 3, which is quite helpful. Question 4, we've then got a bit of writing again, this time about fractional distillation from Unit 7, and you have got quite a lot of lines here when you don't really need them. It tells us crude oil is separated into fractions by fractional distillation. It gives us the boiling point of lubricating oil, naphtha and petroleum gases, and explain how these fractions are obtained from crude oil by fractional distillation. Fantastic. So mark point 1. Crude oil is heated to vaporize. So vaporize is turning from a liquid to a gas. Mark 2. The column has a temperature gradient. That means it is hotter at the bottom, cooler at the top. 3. So gases condense at different levels. So we'd have lubricating oil towards the bottom, then naphtha, then petroleum gases. 4, based on their boiling point. I have used less than half the lines AQA have given me to give the correct 4-mark answer for that question. 4.2 is a multiple choice. Fractions from crude oil can be processed to produce feedstock for the petrochemical industry. Our 2 useful materials from this feedstock are detergents and solvents. 4.3 is a 2-mark balancing equations. You need to firstly give the equation for the complete combustion of C9H20 and then balance. So if we have complete combustion, we are burning our fuel in oxygen to produce CO2 plus H2O. So given those correct formula is our first mark. Our second mark is to balance, so C9H20O2. So we're going to put a 9 in front of here to start with to give us C9 on this side. We're then going to count up the oxygen, so we have 18 plus 1, which is 19 oxygens, and we currently only have 2 hydrogens. We need to get to 20, so I'm going to put a 10 in front of there. I now have 20 hydrogens, so we're happy on both of those. I'm going to count my oxygens again, 18 plus 10, which is 28. So I'm going to put a 14 in front of this to give me 28 in total. You get 1 mark for formula, 1 mark for balancing. We then asked a little bit about impurities. Petrol obtained from crude oil contains sulfur impurities. Why are they removed before the petrol is burned? This is because it produces SO2 when burned, or when it's combusted, which causes acid rain, or you could say respiratory problems for Mark 2. Okay, keep going. 4.5. We're given some information about the number of carbon atoms in kerosene and heavy fuel oil. The student predicted heavy fuel oil is more viscous than kerosene. They were correct. Why were they correct? Well, viscosity increases with molecule size. So the larger the molecule, the more viscous it is. Think about the fact that methane has one carbon atom. It's a small molecule. It's a gas. Whereas something like bitumen, which has many carbon molecules, C100 plus, is extremely thick, used to tar roads. So that would be Mark 1. Mark 2 would be, and heavy fuel oil has larger molecules. So that is why the student was correct. Cool, keep going. We're still on question 4. It's quite a long question, this one. Name the process which produces smaller hydrocarbon molecules and give the conditions. So we're getting 1 mark for saying it's cracking. What a cracking answer. The conditions: steam, high temperature. We're talking 300 to 900 degrees C, or a catalyst. So these are or. So any 2 of those 3 will get you the 3 marks along with cracking. 4.7, we're containing 7 and 8 carbon atoms in our hydrocarbon molecules from cracking. Both will turn bromine water colourless. This tells us that we have an alkene. How are we going to tell which are both alkenes? Well, CnH2n is a general formula. So whichever 2 have the general formula CnH2n, which is in fact the first one, which always feels a bit weird. Cool. We are on to question 5 already. This question is about water. Sewage is wastewater. Sewage contains organic matter. How is it treated to remove the organic matter? Again, lots of lines. We're not going to use them all. Mark 1. Screening of sewage. Or you could say filter to remove solids. We're not going to talk about the solids in particular. So that'll be Mark 1. Mark 2, sedimentation. To produce sludge and effluent. So sludge being solid, effluent being liquid. We then have anaerobic digestion of the sludge. So that's digestion without oxygen, and aerobic digestion of the effluent. So that's with oxygen. 5.2, we're given quite a lot of information here. We're trying to make seawater and groundwater potable, which means it's able to be drunk. We've given information about the 2 processes. So seawater goes through reverse osmosis, and ozone's added. Groundwater goes through filtration and is exposed to ultraviolet light. Before process 1, we have 0.5 moles per decimeter cubed of Na plus and Cl minus, and we're told it's desalinated in process 1. So reverse osmosis, desalinate. This means removes salt. Which pair of concentrations could represent X? Well, if we're removing salt, we're removing NaCl. So it's going to be these 2 at the top, which have the lowest concentration. Both of these have a lower concentration of Na plus and Cl minus. There will still be some present, and not all of it will be able to be removed by reverse osmosis. Explain why the concentrations in the groundwater step between process 1 before and after process 1 are unchanged. And that'll be because the ions are in solution, so pass through the filter. The ions are larger than the filter pore size. Again, 1, 2 for each line. Still on 5. Why did we have process 2 before it's safe to drink? So process 2 was exposing to ultraviolet light. Why do we need to do that? So the water contains harmful microbes, so it needs to be sterilized. Again, 1 and 2 marks there. 5.5. After treatment is sold to companies pure water. It is not chemically pure because it contains sodium ions and chloride ions. What do they mean by pure? It means that nothing, or they mean nothing, is added to the water afterwards. And a wee gas test to finish us off. Describe the test for chlorine gas, give the result. So pass over damp blue litmus paper and it bleaches white. So make sure you've got the test and result for any gas test questions. We're on to question 6 for chemistry at atmosphere now. We've given a figure, a graph, which shows the changes in 3 different gases over millions of years. Explain the change in region A, which is here. So first thing is what is happening? Well, nitrogen is increasing. Why was it increasing 4.5 billion years ago? Because volcanoes were active. These next two use this. I'm just going to keep it above here. Explain the change in percentage of gas in region labelled B. So we're told that's carbon dioxide, so CO2 decreases. Why? It's dissolved into the oceans. This is too early for photosynthesis. So photosynthesis is not allowed as an explanation. The next one is slightly different. So before we explain the change, this time we have to compare the changes in gas, in oxygen and carbon dioxide in region C. So oxygen increases and CO2 decreases. So we have to get both of those for 1 mark. The other comparison is at the same rate. So we're not being asked for a reason why just this time. We're just explaining what is happening. The reason why comes in 6.4, which is photosynthesis is causing oxygen to increase and carbon dioxide to decrease. Our final one here is about the production of natural gas. How were these deposits formed? Where we had plankton, which were buried in mud or sediment, which were subjected to high temperature and pressure over millions of years. So you get 1 mark for 1 word, 2 marks for 3 words, and you've got to write like a full sentence for the 3rd mark. I don't get it, whoever will. Okay, I've just lost this page, that's what confused me. Page 22, we're on to start of question 7. We're on to Haber process, which is very much towards the end of the course. And we're given the reaction equation at the top. What is the source for nitrogen and hydrogen used in the Haber process? 1 mark for each. So air is our source of nitrogen. And for a source of hydrogen, you could say methane or water. Either is fine. How does the equation for the reaction show the atom economy of the forward reaction is 100%? There's only one product, so the atom economy must be 100%. We're then given a figure of the Haber process, or to represent it. How can we separate unreacted nitrogen and hydrogen in box X from the ammonia? So we're going to cool the gases and only the ammonia condenses. So we cool it below the boiling point of ammonia, but above the boiling point of nitrogen and hydrogen. Again, we're moving on fairly quickly now, which is nice. We are on to 7.4, which is our drawing a graph question. Please always use a pencil and a ruler and have an eraser with you to do this. This one's slightly more unusual in that you need to give the scale on the x-axis first, then plot the data, then draw your line of best fit. So using our table at the top here, we've got 60 atmospheres of pressure and 9% yields. That must be our first point here, which means that this must be 60 here. That means that every small square is equal to 10. So I'm going to label every 10th square, as being 100. So 100, 200, 300, 400, and 500. So I'm going to label those all the way along. I'm then going to plot my points. I've already got the top two. So I'm going to start with the third one, 180, which is here, and 25. And then 240 and 31. You do get plus or minus one small square for each point. You do normally have to have 5 or 6 points correct to get the mark. 360 is 40. And 420 is 43. So we've got this part done. We've got this part done. We then need to draw a line of best fit. I have just noticed it's out of 4 marks, which means you probably get 2 marks for all points. 4 or 5 points correct, we'd probably get 3 or 4 points, we'd probably get 1 mark. And I'm going to draw a line of best fit. Now it's important to note there is no point down at the bottom here, so we don't need to include that in our line of best fit. And you should always use a ruler to draw this, or certainly to check your line of best fit to start with. Now our line of best fit doesn't look fantastic here, but we're going to try and get through as many of these points as we can, and we're going to draw something like this as our line of best fit. We're then asked to determine the percentage yield of ammonia at 450 degrees C and 500 atmospheres. So we're already told in the question that this is at 450 degrees C. So we need to find out what's happening at 500 atmospheres, which is here. So we're going to extrapolate our line of best fit up to here and work out where this crosses on this side. Now, to me, that's crossing at 54%, but you would get 1 mark for extrapolating your line, 1 mark for reading the correct value. If your line of best fit is incorrect, you can still gain these 2 marks. We've got our second 6 marker. I did think there was another one coming. This one is about the Haber process, in keeping with the rest of the question. So we've got to explain why these conditions have been chosen here for economical production of ammonia in the Haber process, referring to rate of reaction and the position of the equilibrium. So I'm going to start talking about rate first. So in terms of rate, why have we chosen these conditions? Well, higher temperature will increase the rate as there's more frequent successful collisions. A higher pressure also increases the rate as there's more frequent successful collisions. Adding a catalyst increases rate through a lower activation energy. Cool. What about the equilibrium? Because it asks us to discuss both. So how do these factors play in there? Well, we actually want to have a lower temperature because this reaction is exothermic to produce here. we would prefer a lower temperature to counteract the exothermic forward reaction. But higher pressure is good. It favours the forward reaction as there is less gas molecules or gaseous molecules in the products, and the catalyst has no impact on the equilibrium position. It is also worth considering that high temperature and pressure mean a higher energy needed and higher cost to produce. A compromise is needed, and this is a bit that we need to get into the 5 or 6 marks. Compromise needed. Temperature is chosen to balance rate and equilibrium. So that's why we've chosen 450 degrees C, and the pressure is chosen to balance rate and yield and the cost, and the catalyst allows lower energy costs. No effect on the equilibrium, but it is increasing the rate of production of ammonia. Okay, last question I believe, which is question 8, and this is about our sodium thiosulfate required practical in a little bit of a different way. Why does the mixture become cloudy? It's because sulfur is a precipitate, or you could also say is insoluble. We are then given a method that we haven't seen before, that we're using a light sensor to determine the rate of this reaction. So rather than using our eyes and trying to see the disappearing cross, we're using a light sensor instead, and it gives us the method here. We're also given a graph that shows us a reaction, how the percentage of light reaching the light source from the sensor changes over time for 0.1 mole per decimeter cube sodium thiosulfate. And the question asks us to determine the rate of reaction in moles per second for the production of sulfur at 30 seconds, where you should draw a tangent on figure 7. It also then gives us more information we'll come back to in a second. The first thing I'm going to do is to draw a tangent at 30 seconds, and a tangent is a line which just crosses our curve, but is a straight line where the only point to touch the curve should be here. So this is where a nice sharp pencil will come in very handy. Okay, so I've drawn my tangent here where the only point it crosses is at 30 seconds. I'm just going to extend that as far as I can so that we can get the best points that we can. The next thing we need to do is to choose 2 points at which the tangent, which we're going to use on our tangent to determine the rate of reaction. I always try and find 2 points which definitely are at a junction of 2 of the grid line. So something like this would be very helpful. You do get a slight allowance. I think it's plus or minus half a small square that you're allowed. So to calculate the rate of reaction, we use our gradient, and the gradient equals y2 minus y1, or rise over run. You might work out your gradient a slightly different way, that's fine. Y2 is going to be over here, which is going to be 10, and the x value here is 68. Our y1 value is 52, and our x2 is 20. So we're just going to pop them into our calculator. I'm going to show all the steps just to be extremely clear. But minus 42 divided by 48 is going to give us minus 0.875 as our gradient. The key thing to note, that's percent per second. We are wanting our answer in moles per second. So we need to get from percent to moles. It tells us the percentage of light decreases by 1% when 7.1 times 10 to the minus 5 moles of sulfur are produced. So if we have 1% decrease, that tells us we have 7.1 times 10 to the minus 5 moles. So if we have a minus 0.875% decrease, we're going to multiply both those numbers by the 0.875 to get 6.2125 times 10 to the minus 5 moles per second. I'm just going to round that to 2 decimal place to give 6.21 moles per second. In a mark scheme, you will never get an answer because it depends on the tangent drawn, but we should have a figure around that. Oh, it is times 10 to the minus 5. That's a key thing that people forget that I almost forgot. I got 6.39 earlier, 6.21 now. It is going to be in that ballpark for year 1 as well. I'm going to go quite quickly because it is almost lunchtime. 8.3, explain why the rate of reaction changes between 0 and 60 seconds. Answer in terms of concentration, use figure 7. So we're going from 0 to 60 seconds. Why does it go down like this? We could say, or how does it change? Well, the rate decreases as the concentration of reactants decreases. We're then given that same graph again, and we're told this time that we have an excess of sodium thiosulfate solution. The line of best fit on figure 8 is horizontal between 80 and 120 seconds. Why? And this is because all the acid is used up. If sodium thiosulfate is in excess, our hydrochloric acid must be our limiting reactant and will be used up fully. We're then asked to sketch lines, show the results you predict when we've doubled the concentration. If we increase the concentration, we're going to increase the rate of reaction. So we're going to have a steeper line starting at the same point. Again, use a pencil. However, it's going to end at the same point. We are still going to produce the same the same here, but the rate has increased. We still have our excess of sodium thiosulfate. We still are limited by the hydrochloric acid. You get 1 mark for kind of this section here is worth 1, and 1 mark for leveling off at the right point. So as long as the line is more steep, you are happy. We are almost at the end here. We've got a couple of multiple choice questions, which is quite nice. How could they improve the method so that the same percentage of the lights reach the light sensor rather than being different on different days? They could stop other light sources reaching the light sensor, so maybe put in a dark box. The student improved the method so that they receive similar results on different days. What name is given to similar results on different days? It means we are repeatable. Anomalous would mean there's one that's already off. Reproduce when other groups got the same results. We are repeatable this time. We are on to the final 2 questions. We've got 8.8. Which expression represents the relationship between the volume of sodium thiosulfate and the mass of sulfur? So sodium thiosulfate is here. Mass is here. They are directly proportional. These other values, they're not the same. It would be this way. It's not very much less, and it's not approximate. Finally, this is kind of a weird question. It's a bit mathsy. Determine the simplest whole number ratio of the volumes of sodium thiosulfate solution to hydrochloric acid, which completely react with each other. I decided to find at any mass. So I went for this mass here at 0.05 grams of sulfur. I drew a line and worked out where this crossed. I maybe should have done that with a ruler, but I drew this line and I drew down. to where it crossed. So I got to make 0.05 grams of sulfur. I need 15 centimetre cubed of sodium thiosulfate and 60 centimetres cubed of HCl. To work out this ratio, I've got 15 to 60, which when I divide it down to the simplest ratio is going to be 1 to 4. You get 1 mark for using the figure, you get 1 mark for the correct points chosen, and you get 1 mark for your ratio. Any questions, do let me know.